hear me?
Sir.
Okay. 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 So this document is visible.
Sir.
Okay. So actually, you see, we have already covered most of the parts of this chapter. Okay. So this first chapter actually, your actually to introduce you with different kind of number system first, then different kind of complement, one complement, and different kind of representation of floating and integer numbers. Okay, and then this is the last section actually of this chapter. Okay. So in this section, in this last last section of this chapter, actually, we will try to learn uh, different codes. Okay, so what are different codes are there? There are actually BCD binary codes like BCD, NBCD codes are there. XS3 codes, XS3, there is a code name is XS3 is there. Gray codes are there. Alphanumeric codes are there. Okay, so today actually we try to learn these things. Okay, Samojit, unmute yourself. Okay, so before starting this section, okay, so what we already know there are binary number system, decimal number system, hexadecimal, and octal number systems are there. We know the conversion between this number system from one to another. Okay, we understand that what is ones complement, twos complement, eights complement, seventh complement, ninth complement, tenth complement, 15th complement, as well as 16th complement. So all the complemented methods we know. We already know that how I can anyone can represent any floating number, okay, any integer number in any of the number system. Okay, next. So basically, this after knowing these things, what else we need to know from this chapter? We need to know that uh, apart from this kind of number system or binary numbers, like all kind of number system, what are the codes that are available? Okay, using number system we can represent a number. Okay, but that in our keyboard there are characters, or rather I say there are symbols apart from the numbers, right? So there are alphabetic uppercase, lowercase symbols. There are special character symbols. Okay, so basically only representing the numbers is not going to solve our problem. We need to represent these characters, these symbols also. Okay, so for that purpose we have different codes. Okay, so step by step we proceed and we try to understand. So first, the, the, the first one is actually your binary coded decimal. Okay, so what is actually binary coded decimal? So the binary coded decimal is you can see from this table. So in the left side there is a decimal digit. Okay, so there are 0 to 11 I have noted here. Okay, and this binary coded decimal BCD code I have represented for each of the decimal digit. Okay, so BCD code also known to us as a 8421 BCD code. Okay, why 8421? Because this is a weighted code. BCD code is a weighted code. Weighted code means each digit. Here you can see each digit has different weight. Okay, so first of all, BCD code. What is actually BCD code? This is actually binary coded decimal. So this is here you can see there is a part, one part is binary, another part is decimal. Okay, so this is a decimal. You can say this is a decimal coded in binary form, right? So basically, decimal to binary conversion is happening here. But what is the difference between decimal number system? Means if, we already know that we can easily convert any number from a decimal digit to binary. Okay, so by dividing two, noting, taking note on the your what is a quotient, what is remainder, like this. We already knows this. So what is actually difference in this case in BCD code, binary coded decimal case? This is actually your weighted code. First point will be noted. It is a weighted code. Okay, what are the weights? The weights are like 8421. Why it is 8421? Because there are only 4 bits. This BCD code is actually 4-bit code. Okay, so 4-bit combination are used for representing single decimal digit. Okay, so that's why this is a 8421 code. So single decimal digit 0 is represented using this BCD code. Then this representation is 0000. Okay, the single decimal digit 1, it is represented 0001. Okay, so in this way this can be represented, this can be used, this formula can be used from 0 to 9. Okay, so from 0 to 9 it is 1001. Okay, this is a representation of 9. Now you can ask me that, sir, I can also represent 10 by using this 4-bit combination, right? Because what will be that combination? 1010. So 1010 is nothing but 10. But this is true for binary when you are using a binary number system. But when you are using a BCD code to represent a decimal digit, you need to follow this 4-bit combination format, this 8421 combination format. So 8421 combination format is nothing but it's the weight of each digit, and BCD code has 4-bit BCD code has 4-bit representation. Okay, so using 4-bit it can only represent single digit. Okay, if there is 2 digit in decimal number, then it is represented by 8-bit combination, because 4-bit for first digit 1 and another 4-bit for second digit 0. So you can see here 0001 0000. So this is how BCD code is can be represented for different decimal digit. So suppose if I take an example like 1111, triple one. So that means what I have to write here. So 0001, then 0001, then 0001. So you can understand that if the decimal digits are increasing, then the number of bits, required number of bits is also increasing. Okay, so this is the disadvantage of this BCD code, because using BCD code, if anyone wants to represent a bigger decimal digit, say 10,000 or 11,000, then 11,000 means there are 11,000. So there are 5 digit in decimal. So corresponding BCD code will have 5 into 4, 20 bits. So you can understand that 20-bit representation is not a very good representation, efficient representation for 10,000. Okay, so binary with respect to the size, binary representation are having a good at means ahead of this. Okay, with respect to the size, but this code is also has some means what you can say, this code is has also has some advantage over binary one. Okay, so let's discuss that thing. So one disadvantage of this code is it requires more number of bits with respect to binary. Okay, but there is advantage also. Okay, so going to that part, one thing you need to note here, that using 4-bit. Okay, so that the topic that was I was discussing, the using 4-bit, you can represent a symbol, 16 different symbol, right? 2 to the power 4, that is 16. 0 to 15 you can represent. Okay, but in 8421 BCD code, only 10 of these are used, right? 0 to 9 are used. So you are not using 10, 11, 12, 13, 14, 15. Okay, so what about this remaining 6 combination? These 6 combinations are invalid in 8421 code. Okay, this 6 combinations are invalid in 8421 code. Okay, so this is the thing. Okay, so are you getting my point? Means what I am trying to means represent here. I am trying to represent a BCD code, and okay, so which is a weighted code, which can be which is basically you can say that this BCD code can be used to represent a decimal digit of any decimal digit. Okay, but it take help of 4-bit notation. Okay, so 4-bit it used for representing a single digit. Okay, so if there are 10 decimal digits, then 10 into 4, 40 decimal, 40 binary digits are required. Okay, so this is the great disadvantage for this BCD code. But this BCD code has also another advantage, that is that this BCD code can be used very efficiently for addition of decimal numbers using your computer. Okay, BCD addition. So BCD code basically used for different decimal value, decimal addition. Okay, so that means suppose you are adding a value in two numbers. Okay, so if when you are adding a two numbers using binary number system, okay, then what you have to do means I will show you in this next chapter. You have to follow some certain rules, but in case of BCD addition you don't need to follow those rules, because directly you can get the result. Okay, so means for arithmetic operation, this BCD code has a great advantage over binary one, because that's why some cases this BCD codes are used. Okay, so let me go to the example one first. Okay, so to express first here you can see that to express any decimal number in BCD code, simply replace each decimal digit by appropriate 4-bit code. Okay, so that means if any number is given like 23, so what you have to do, you have to represent 2 by 4-bit combination, you have to represent 3 by 4-bit combination. So here this thus 23 decimal can be converted to BCD form using this directly. So everyone can, I think everyone can transfer this decimal number to BCD number. So this is quite straightforward. Okay, so advantage that I was discussing, advantage of BCD code over binary are, it is very simple. Okay, it's, because you don't need to, when you are getting going for bigger number, you don't need to means you don't go to what you need to do. Means suppose if I represent triple one, okay, in binary, so can you directly represent triple one? You cannot, because you have to means you have to take the help of these two methods that I already described to you previous in my previous class. Okay, so you have to take those any of those methods and calculate the corresponding binary combination. Right? Is it right to all? Means if I say that just convert triple one to the binary, can you do it quickly?
ना सर, टाइम लगेगा.
Exactly, because obviously maybe you can take this one, this step. Okay, so you write all the weights consecutively, sequentially. Okay, then you just try to calculate which should be zero, which should be one, like this. Or you can take help of this double method, means this quotient remainder method. Okay, so it also takes some time. Okay, but the representation this number into this BCD triple one in the BCD is very straightforward, very simple. What you need to know? So you need to know what is the representation for one. So you know that 0001 is the representation for one. So you can directly represent this number into BCD. Okay. So 00001. So you can understand. So this is the first advantage of this BCD code. Okay. So BCD code is advantage of BCD code over binary is very simple. Okay. We do not have to perform successive division by two, write the remainder. We simply have to know the codes for the 10 basic decimal digit. Then we can convert any decimal number into equivalent BCD number. The disadvantage are it requires large number of bits than binary equivalent. BCD arithmetic implementation is difficult as compared to the binary. Okay, so yeah, I will show you this thing in the next chapter. Okay, Okay, next code. Next are BCD code is sometimes used in different aspects of our daily life, maybe, but there are different weighted codes also available that are not mostly used, but you need to understand that what is that thing. Okay, so there are actually different weighted code are available like 8421. Okay, so this is just for your information. So 8421, 5421, 7421, 2421, 5211. These kind of weighted codes are available in the literature. Okay. Okay. So you can see that I have shown here the representation of 9 decimal digit into those numbers, and from there, some points you can remember. So the points are like this. The 8421 code utilizes the natural weights for representation of the binary numbers. Hence, it is popularly known as natural BCD, natural binary coded decimal. Okay, so basically there is two terms. One is BCD, one is NBCD. Okay, and BCD and NBCD are actually the same thing, but their representations are very. Just one second. Okay, so BCD BCD and NBCD, their representation are quite same, but the thing is, in the literature there is a different name. Okay, one name is NBCD, that is for only 8421 code, and one name is BCD, that is 8421 BCD code. Okay, so there is no difference as such. Okay, so next thing is that this term is also important, self complementing. Okay, so this is a one technical term that can the means most of time you can see, you can face like what is self complementing code. Okay, so this kind of question may be asked in different scenario. Okay, give me the example of self complementing code. Okay, so what is actually self complementing code? A code is said to be self complementing if the binary representation of a decimal number n in that code is the ones complement of the decimal number 9 minus n. Okay, so basically a self complementing code. If see the example here, suppose I am using 2421, this thing I'm using 2421 here. I am trying to represent 4, so this is actually the representation of 4. Okay, so if this representation is equal is one's complement of representation of 9 minus 4, so 9 minus 4 is nothing but 5. Okay, so for these two combination, now you see, so combination of 4 is 0 1 0 0, and combination of 9 minus 4, that is 5, equals to 1 0 1 1. From these two combination you need to take a decision whether these two are complement of each other. If the question is yes, means if the answer is yes, then this code is 2421, this coding system is a self complementing code, means it is complementing itself. It is complementing itself to get the number, means complement of suppose nines complement. We already know nines, what is nines complement. So in the nines complement method, the complement of 1 is 8, complement of 0 is 9, means nines complement method, complement of a number is a 9 minus that number. Okay, but tens complement is 9 minus this number plus 1. Okay, so don't go to the tens complement, concentrate on nines complement. So nines complement of a number is 9 minus that number. Okay, so that things you need to take a decision. For suppose you are using 7421, now you are using suppose 7, and let me use 5421, then now we are using 5421. So what is the representation of 4? Representation of 4 is 0 1 0 0. And what is the representation of 5? Representation of 5 is 1000. Now whether these two representations are one's complement of each other, the answer is no, right? So answer is no, that means this is actually not a self complementing code. Okay, you understand? are you are you getting my point?
Yes, sir.
Okay, so as this is actually the way we can calculate, or we can actually understand that whether a code is self complementing or not. Okay, so what about 5211? You tell me. From this table is visible to everyone. So from this table, you now try to tell me that whether 5211 is your self complementing code or not. Okay.
Yes, sir. It is
Yes, right.
self-complementary.
It is self complementary, right? So, but what about 8421?
Not.
It is not, right? Okay, so next is so here it is weighted code 2421 5211 are self complementing, whereas these are not these are not self complementing code. So I hope that you are not giving the answer from this note. You have already calculated by yourself. I hope that thing. Okay, let me go to the next part. So next part is how we can convert a BCD number into a binary number. Okay, so suppose a BCD number is given. So this is the example of a BCD number. You can see here. This is a BCD number. So this BCD number has both two parts, integer as well as fraction. Okay, so this BCD number need to convert into a decimal number. So what you have to do first, you understand that this is a one, this is for one bit, this is for another bit. So this is two. So you write two. What is next? This is 8 plus 1, 9. So 9, then fraction. This is a decimal point. Okay. So basically this is not a decimal. This is a BCD point. So BCD point, then this after BCD point, this is 7 and then 5. So this is actually the number in the decimal. So you are getting a decimal number directly from this BCD combination. Okay, this is very straightforward. Once you get the decimal number, you can directly convert into the binary number because you already know the methods. Okay, so 29 is converted here and 0.75 is converted to this. So I have not shown this method because we already discussed this thing. So from we can directly convert that number into a binary. The point that you need to remember that here, whenever you are converting a BCD number to binary, so if you can see that this you can understand or you can visualize this thing that this given BCD number is already in the binary format 0 0 1 0 1 0 1 0 1 1 0 1 0 1. Then why should I convert it into binary? It is already in binary. But remember, it is not in binary format. This is a binary coded decimal form. Okay, so that means if here you need to take out the decimal number. Once you get the decimal number, then you convert it to the binary number. Okay, so you can see this. This is the actually the binary combination of this number. So you can understand that only there are very less number of bits are used to represent that decimal. Sorry, to represent that BCD number. Okay. So similar to that, this just opposite thing. When you are converting a binary number to BCD number, what you have to do? A binary number is already given. From that binary number, you need to means get the decimal number. So once you get the decimal number for each and every digit, you can represent by 4-bit combination. Okay. So this is suppose this is the binary number. Okay. You can see here in this copy. So this is actually your binary number. Okay, so from this binary number, if you need to convert it to into the BCD number, then what you have to do, you need to take the decimal number. Okay, so what is the decimal number? From here you can calculate. How you can calculate? I have already shown you in previous section. You need to write weight method. You can take the weight method. So you write the weight of the each digit. Then if there where is 0, you just don't take that note, and where is 1, you just take a summation of those weight. You need to sum. You need to take a summation of the weights where the bits are 1 actually. Okay, so this is true for integer as well as fractional part. So you can directly get this 171.625 number from this combination. Can you get it? Yes. Nila is already is given the answer. So one, two, three,
Sir,
four. Okay, yes. Hello.
sir, BCD code can only be found out for decimal numbers.
Yeah. This is not actually true, but you can means as you already we know that you can convert any number to any number system, right? So suppose I am giving a hexadecimal number. I ask you convert it to BCD. That is also possible. But in normal cases, from decimal number, we means we take the decimal number system as a reference because we normally take the decimal number system in our daily life. So for that purpose here, I have shown here decimal conversion. But you can take a hexadecimal number. Then what you have to do? Take a hexadecimal number, convert it to decimal number, then convert it to the BCD. So this kind of combination, permutation combination you can do, but those are in your hand because you already know. Means if I give you a tough example like I'm giving you a octal number, okay, then I ask you that what will be the BCD code. So you can also convert that octal number to decimal number. Then from decimal number you are getting, when you are getting in decimal number, so you know that you are getting each digit. Okay, so that each digit, from each digit you can easily convert that number into BCD. Okay, but point to be noted here, in whatever system, in whatever number system the number is given, suppose a given number is a octal or hexadecimal or binary. Okay, you need to convert it to decimal first. If you try to convert directly to BCD, then there will be a error because you cannot convert it. Because as you see from this table, uh, let me go to the table. As you see from this table, this BCD table, that BCD table is for decimal digits. Okay, that means for decimal digit, when you get the decimal digit, then only you can convert it to BCD. It is not for means octal digit or hexadecimal digit like this. So when number may be given in any number system, but you need to convert it to decimal, then you can convert it directly to BCD. That is the point. Okay. So this is the way we can convert any number to means we already know that we can convert any number to any number system, other number system. So, and this is the way to convert BCD to binary and binary to BCD. But whenever I am doing BCD to binary or binary to BCD, I need to go first to the decimal number system, because if I cannot means if that is required basically, you understand from this example, you cannot directly convert it to this number. Is it possible to convert that this combination to directly this, means from this combination you cannot realize that what will be the binary number, this binary combination, because this is not possible, because in your back of mind you think that this is only 2, this is 9, this is 7, this is 5. So this is back of your mind calculation, so this is 29.75, then only you can get the binary. Okay, so this is how the things are happened here. Okay, so try by yourself how this is the problem for your side. How many bits would be required to encode a decimal number 0 to 4? There is 9999 in straight binary. Okay, in straight binary means normal binary and BCD code. Okay, so the question is how many bits are required if you try to convert a number 0 to 49 into a binary format or in BCD code format. Okay, so how many bits are required? So you just need to answer the number of bits. And next question is what would be the BCD equivalent of a decimal number 27? Okay, in 16-bit representation. So if it is still like 16-bit representation and you see that the number 2 bit, two 2-digit decimal number, then you can add 0 at the left side, right? So basically 27 is are you getting my point? 27 means records 8-bit BCD, but you need to represent by 16. So you need to add 0 at the side. Okay, so that's the problem. Okay, so going to the next code. So this is all about BCD code. So what actually we need to understand from this BCD code and this weighted code. First thing is BCD is a weighted code. There are 9 valid decimal digit representation in BCD. Okay, and 4-bit representation, 8421 weight of each bit. Okay, and this BCD code can be represented. Yes, I'm getting a answer. Okay, so there is a concept of self-complementing code also. Okay, and there is a conversion method from BCD to binary, binary to BCD. So I'm getting one answer from Sirish Raghuvanshi. Okay, so, you when you are giving any answer in the chat box, don't and write answer privately. Just write it for everyone, so everyone can see the you see your result or your question or your answer like this. Okay, so what I cannot understand these combinations. Uh, this two why there is two in the MSB. Okay, Shri.
सर वो क्वेश्चन नंबर 2 का आंसर है वो एक जीरो वो टाइपिंग में थोड़ा ज्यादा हो गया वो लेफ्ट साइड में
ठीक है ठीक है।
वो टू से क्वेश्चन
क्वेश्चन
नंबर
नंबर 2 में क्या क्वेश्चन था? Which one is question number 2 here? I cannot understand. This first example. Okay. Kamojit is giving answer that's 0 to 999 binary. They are equal for 14 bits and there is 16 bits. Exactly. Actually, yes. How you are Kamojit you are calculating? Because 2 to the power 14 means you need to represent this number, this
So actually,
9999. Okay. So
I am doing log base
hmm,
2 of 9999. So it
exactly
is
you can
coming
get that
13.2.
from that.
It is coming 13.2. So we
Hmm,
need something more than 13.2. So 14 will be the answer.
exactly.
And for
14 will be
that,
the answer. Right.
for each digit for BCD, we are taking
BCD
4 bits.
4
4 bits for
exactly
each
4
digit. So 4 4 just 16.
exactly correct correct. So basically you understand if I give you the hint of this problem, then means you need to represent a number that is 9999. Okay, so this number actually you can get this number from this is a decimal number. Okay, so and so you what will be the combination for this? So this is the question actually. Okay, so what will be the number of bits here? Okay, so you can take the log of this. Okay, so you can get the complete result from there, or bit or you can take the power of 2. Okay, 2 to the power, so 2 to the power 10. So 2 to the power 10, what will be the 2 to the power 10? 2 to the power, let me give you 2 to
1024.
the, yes,
1024.
1024. Okay, so 1024 you are getting. So then how if I multiply by here, just make a division. Let if I take a division by 1024, so what will be the value? 9999
9.7.
9111024. So 9.7. Okay, so that means 9.7. So 9.7 means we need to multiply that digit. So 10 digits are there for then you need to multiply it 9 times. So do 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. 2 to the power 3 means 8. Okay, so 2 to the power 4 means you need to take 4 bit for this. You require 2 to the power 4. So 9.7 cannot be directly represented by means in the power of 2. Okay, so better we take 2 to the power 4 so that I can take all the combinations. So 2 to the power 4 means there are 4 bits, there are 10 bits. So total is your 14 bits. Means by if you take this for this type of answer means you can take this method for your answer, and there is another if you take a log of this number. Okay, so log I don't think that there are directly show you algorithm result, but if you take the log you can get the number nearly equals to 13.2, right?
13.2.
Yes. So just let me use my calculator. Okay, so going to the next part. So going to the next part is XS3 code. In XS3 code, okay, just one second. Okay, so in XS3 code, this is again this is a kind of code which is unweighted first of all, and there is no definite weights are assigned to each position. Okay, as the name suggests that this code is obtained by adding three. XS3 means there is extra three. Three is so it's add by adding 3 to each decimal digit and converting it into the binary. Okay, so basically if a number is given in a decimal number that is 0, then corresponding BCD code we already know And what will be the excess 3 code? Just adding 3 with this number. So 0 representing in excess 3 code is 0011. So you have to add 3. So 0 plus 3 is 3. So 3, this is the combination for 3. 1 plus 3 is 4. This is the combination of 4. 2 plus 3 is 5. So this is the combination of 5. In this way, you go and you can take the excess 3 code for 0 to 9. So if it is 10, so means if I take next example is 10. So now, so in that case also you have to take help of 2-digit combination. Right? So it will be 0001, then 0000. So similarly here it will be your 4 means 0, then 3, 1. So like this will go on. Okay, so this is actually self-complementing code. Okay, so why it is self-complementing code? So you can understand that this combination here 4, and you see the combination here 5. This is the complement of each other, right? So that means it's a unweighted but self-complementing code. Okay, so 5211 means previously we have some weighted code self-complementing, but this is an unweighted code self-complementing. Okay, and for this also example are given like this number. Suppose you need to find out a excess 3 code for a given decimal number 597. Okay, so 597 like this 597. So you need to add 3 for each digit. So you are getting 8, 12, 10. Okay, so 8 is this, 12 is this, and 10 is this. Okay, so 597 is actually can be represented by 597 can be represented in this way. Okay, so I think this is not actually the correct one. Yeah, this is not, this is good for here. Okay, so suppose I am giving your number a 10. So what you need to do, you need to add 3 with this, and you need to add 0 with this. Okay, so when you add 3 with this, you are getting 1 plus 3, that is 4, and 0 with 3, 13. Okay, so actually the thing is this, but the representation is not, there is a space, no space is actually required like this. Okay, so this will be the representation of the number 10. So similar to that, here for 597 the representation is for 8, 12, 10. So for 12, what you are getting here, you are getting this. So this is for 8. Okay, so let me show you directly. This is the given number, and this is the combination for this given number. Okay, okay, is it okay to everyone? Means 597, the given number is 597. So you need to convert that number. 5 plus 3 8, 9 plus 3 12, 7 plus 10. So you are getting this number. So you just write down in a compact manner. 5, 9, and 7. Okay, so this is the number 10. Then you need to take this is represented BCD, and you need to add 3 with each digit of like this is for this number. Okay, so this session will end with, so write down your ID for this session, and next I will start the next session. uh, Nilanjan has given the answer. The 9999. This the question is how many bits are actually you required. How many bits actually you require to represent for this number 9999, right? So this is the actually the procedure for taking. Suppose here it is 9999. So for any arbitrary number, okay. So you can how you can take that thing. So you need to suppose a number is given is your 9999. So you need to represent this nearest number with the power of 10. Okay. So with power of 10, if I represent this number, then what will be the value? So that will be actually nearly equals to 10 to the power 4, right? Because I cannot get the exact value. So this is nearly equals to your 10 to the power 4, right? So if you get this value 10 to the power 4, okay. So similar to that, what you have to do, you have to take this means in the binary representation, the basis value is 2. So 2 to the power n. So 2 to the power n, that n you need to find out that number of bits. So 2 to the power n, that should be equals to that 10 to the power 4. Okay. So number is your 9999 here. Okay. So it is nearly equals to 10 to the power 4 because 10 to the power 4 is 10 this. Okay. So the 10,000. So this is nearly 9,999. You cannot get if you need to represent the decimal number with the power of 10. Similar to that means suppose there is a binary number. So that binary number having n bits. So I am representing that n bit with the power of 2 to the power n. Okay. Now from this part you can now you calculate the value of n. So I think that you can calculate the value of n. Now calculate value of n. Okay. So how many what is the value of n? Means suppose any given number, some like here the number is 9999. If the number is this like this, okay. So how many nines are there? Oh, 1, 2, 3, 4, 5, 6, 7. Okay. So 7 nines are there. So that means I need to take a number 10 to the power 7. Okay. So your it will be nearly 1, 0, 3, 4, 5, 6, 7. Okay. So if the number is like this, okay. Okay. So if the number is like this, so then your that number can be represented. So that number can be represented in the power of 10 because you are using a decimal number. So power of 10 you need to represent. So that number can be represented in the power of 10 nearly equals to 10 to the power 7. So this is the number, not exactly the same 9999, but nearly to that number. Okay. Okay. So after that, what you have to do, the question is how many bits are required to represent this number. So that suppose here the number of bits are there. Okay, right? So you don't know the how many bits are there. So that bits, suppose these bits are combination of n. Okay. So n to n minus 1. So the bit starts from n minus 1, right? To like this to 0. Okay. So if you are getting a bit number 16, that means 0 to 15. Okay. This kind of thing will happen. Okay. So 2 to the power n. So 2 to the power n equals to 10 to the power 7. 10 to the power 7 here. So take a log and you can get the result. So n will be So n you will be like, so if you take a log, then what you will get? Log 7 by log 2, right? 7 divided by log, sorry, log 2. Okay, so basically you are getting 7 divided by, what is the log of 2? 0 point, what is that value? 0.3, something like. What is the value of log 2? Everyone is busy with giving attendance. I am asking what is the value of log 2. They are giving Siddharth Mondal 191001001. So I use 19100 here.
So 0.3010.
Okay, okay. Okay, so what will be your result here? So 7 by 0.3090, what will be the result?
T point 2558.
Okay, so that means you require actually 23.255. That is nearly equals to your 24 bits. Oh, sorry. That is nearly equals to your 24 bits. So you actually, to represent this big number in binary, you require 24 bits. Okay, so first bit position will be 0 and last bit position will be 23rd. So that's why I have represented in this way. Okay, so actually you require 24 bits. This is how you can calculate for any given number. Okay, for any given number, any given decimal number, you can calculate how many bits are required for that to represent in binary. Okay, but now the question is again, there is how many bits required for BCD. So how many digits are there? There are 1 2 3 4 5 6 7 digits. Okay, so I just change this format, 999. Okay, so this is actually the given number.
7.
Okay, so 999. Okay, so for BCD, you require 4-bit combination, 4 multiplied with how many bits? 1 2
7.
3 7. 7.
28.
So 28. So so you require 28-bit representation, 28 bits representation for BCD and 24-bit representation for binary. Okay, so this is the thing. So in the XS3 code, so this is actually not, this is not a weighted code, unweighted code, but this is a self-complementing code. Okay, for any given number like 0 to 9, I have shown for 10. Suppose number is 10. So for 10, what you have to do? You need to represent it BCD code. So this is the BCD representation, and now 1. So that means 1 plus 3 4, 0 0 plus 3 is 3. So 4 3. Now make a compact. So 4 3 is the, this is the representation for 10. So similar to this, if a number is 597, so you need to add excess 3 for each digit. 5 plus 3 8, 9 plus 3 12, 7 plus 3 10. So you are getting these 3 valid digits for excess 3 code. Once you get this thing, so 8, I am representing 8 here. This is the combination 8, this is combination 12, this is combination 10. So don't confuse here, means it is little confusing that this is 12, that means we again required to represent it in a 4-bit 4-bit plus 8-bit combination. Now this is the number you are getting, this is the final combination. So here you can represent 12 by 4-bit combination. So 12 it is represented here like this. It is not represented here like if I show you here. So for suppose 11, so 11 means here this, you understand. So this is for 11, but in if I go to this excess 3, so 1 plus 3 is 4. So this there is no this should be compact. So this is the 11, and now if I show you for 12 here, so this is for 12, and here it is 3 plus 1 plus 3 4 0 1 0 0, then 2 plus 3 5 0 1 0 1. So you see for 12, when it is in decimal digit, it is represented excess 3 code by this combination, right? But here in this example 597, when you are getting a number 12 after adding 3 with 9, at that moment you don't go to represent like this, you just simply represent by 1100. Okay, so this is the thing, this is the given number, but this 8 12 10 is not the given number. So 8 12 10 you can represent by this combination. Okay, don't confuse here. Understand? Right? You get my point?
So what is the meaning of unweighted or weighted? Why use
Unweighted and okay, unweighted means suppose BCD is weighted, right? So means what is the weight of BCD? 8421, right? So just I am writing the means the weight. Okay, just you can see, note here 8421. Okay, and what is the combination for 1? 0001. So that means you don't need to take the consideration of 842. You need to consider only 1 here. So when you considering this one, the weight of the digit, weight means weight of the bit position. Okay, so 0th position weight is 1, first position weight is 2, second position weight is 4, third position weight is 8. Okay, so this is actually position value, and this is the digit, so you need to multiply this thing. Okay, so 8421 you are getting as a 1. So how I am getting 1? So this is the combination. So let me show you in this way. So this is your BCD code 0001, and corresponding weights are 8421. Now what you have to consider, you don't need to consider 842 because the value is 0, means this is how we can calculate 0 into weight. So 0 into, this is for MSB, then plus again 0, there is another 0, 0 into 4, then plus, then again 0, 0 into 2, then plus 0, then there is 1, 1 into 1. Okay, so now you are getting what? 1. Okay, so this is true for each and every case. Suppose I am taking 1001, so here I am writing 1001. So what is the weight? Weight is same, 8421. Okay, and now calculate. So 1 multiplied with 8, then plus 0 multiplied with 4, then plus 0 multiplied with 0, plus 1 multiplied with 1. Okay, so what you are getting? You are getting 8 plus 1. Okay, that is
से
9.
ये हम लोग ऐसे भी तो देख सकते हैं ना कि ये सम डैपल वाला वो है, क्या बोलते हैं, प्रोसेस 8+1। अगर 9 का बीसीडी कोड निकालना है तो 8421 में 8+1 करेंगे तो 9, और 42 का प्लेसेस अगर 0 से रिप्लेस कर देंगे तो।
एग्जैक्टली वैसे भी कर सकते हो. तो बट द पॉइंट
लेकिन
इज
ये
मीन्स
सिर्फ 0 से 9 तक वैलिड रहेगा।
एग्जैक्टली बीसीडी कोड 0 to 9 इज वैलिड. ओके, उसके बाद जब भी कोई दूसरा नंबर होगा, देन यू हैव टू take that number
हर
as
डिजिट
a
का
part by part.
रिप्रेजेंटेशन देना होगा।
Exactly. Yes, part by part. Okay, now the thing is that here it is weight. You see this weight is common for, that is same for both of the number. So if whatever number you are taking in the BCD, you need to follow the weight format, and weight format is constant. Okay, so just unmute yourself and unmute yourself. Okay, so wait format is constant. Now you see in this XS3 code, okay, if you follow this wait format 8421, then what you are getting here for this example. So 8421, so you are getting actually 4 here, right? But 4 you are actually representing 1, not 4. So that means the wait method is not valid for this XS3 code. You can check for each and any of the digit. Okay, suppose 1010, so 1010 means 8 plus 2 10, so actually you are representing 7. So the wait method is not valid for XS3 code. So whenever in any of the code this wait method is not valid, then that code is your unweighted code. Okay, this is the reason why it is called unweighted. Means the weight is already we know that there is a weight for each and every position, right? 2 to the power 0, how these weights are coming. So if try to think in the binary, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So in this way you can get n number of weights. Okay, no problem. But in case of BCD you need to take only 4 weight, 8421. And now for XS3 code, there if you cannot give any weight format here, because it is not actually following any weight format. Okay, so that's why it is known as unweighted format. So I think I am clear. And one another thing that I have mentioned, that don't get confused over this combination. Means whenever a number is given, you need to add 3 for each and every digit. After adding 3, if you get a combination of 2-digit number like 12, 10, 11, like this. Okay, so maximum what you can get 9 plus 3 12, 8 plus 3 11, 7 plus 3 10. So in a 2-bit combination you can get 10, 11, 12. At those cases, don't get confused that you need to represent those digits or those numbers with the help of 8-bit combination. Okay, what you have to do, you have to just convert that number into a straight binary format. So 8 plus 4 means this is the 1100 for 12. 10 means 1010. Okay, so this is the code for 597. Okay, so going to the next part. So there are 2 examples. You just try to solve those examples by your own. Okay, so whatever examples I am giving, okay, you need to solve them. Okay, so the concept will be much clear at your side. So next code is your gray code. So gray code is again a unweighted, because you cannot give a weight to each of the any digit, but it is not actually following any weight format. So again unweighted code, that is gray code. and and it is not used for normally arithmetic operation. Okay, so if any code is not weighted, means if any code is not following a particular format, okay, that means you need to represent a number in a particular format. If that in that code format it is actually not actually following any weight, then you cannot use them in any arithmetic operation. Okay, so this actually gray code is not for arithmetic operation, it is for other purpose. Okay, so when we are talking about gray code, so then one technical term that we need to understand, that is Hamming distance. Okay, what is Hamming distance? Hamming distance is nothing but the number of bit position change while in a consecutive two numbers. Okay, in a consecutive two numbers, a particular code. Suppose I am working with binary format. Okay, so in a binary format, suppose if I consider consecutive two numbers 0 and 1. Okay, so now how many number of how many bit position have changed here? So you see in a 0 is 000040, and in 1 is 0001. So there is one bit position has changed, that is LSB position has changed 0 to 1. Okay, so how many bit positions are changed in a particular format will give you the Hamming distance. Okay, so for suppose binary 4-bit code. Now how to calculate Hamming distance? Suppose binary 4-bit code, I need to check for each and every consecutive digit combination. So 0 and 1, there is a Hamming distance is 1. Now calculate Hamming distance for 1 2. What will be the Hamming distance? So you need to see what, how many bits are changed here from 1 to 2. So 1 to 2, there are two bits are changed. You see 0 to 1, it was 0 to 1 and another was 1 to 0. So that means there are two bits have been changed. So that means Hamming distance is your 2. Okay, let's go to the next one, 2 3. So from this combination you can see Hamming distance is 1. Okay, so 3 4, again 3 4, Hamming distance is 3. So you see that as I go forward, as I am taking a different example like 0 1 or 1 2 or 2 3 or 3 4, I am getting a different kind of Hamming distance, not a constant Hamming distance. So whenever in any particular code the Hamming distance is not constant, that code is not a cyclic code. Okay, that code actually your non-cyclic code. Okay, so binary 4-bit combination code is actually non-cyclic. Okay, are you getting my point? There Hamming distance. Hamming distance means, suppose in a BCD code. Suppose I am working with a BCD code. Okay, so let me give you this example. I am working with a BCD code. So in the BCD code, how many bits have been changed while you are going from 0 to 1? Okay, from when you are going 0 to 1, how many number of bits have been changed? What will be your answer? Give me answer. What will be your answer? What will be the Hamming distance when I am going from 0 to 1?
Sir, 1.
Okay. Next, if I go from 4 to 5, what will be the Hamming distance?
1.
1. But if I take a different example, let me take this example. 1 and 2. Okay. So what will be your Hamming distance? So 1
2.
to 2. 2.
0.
Okay. So you see, if you take a different example, you will get different example, different Hamming distance. So you are when I am taking 1 2, I am getting Hamming distance 2. Okay. When I am getting taking 4 5, so it is 1. Okay. Suppose I am taking this combination, this 8 9. So it will here you see there are 4 bits are changed. So this is not a console, this is not a cyclic code. You understand? This is not a cyclic code. So you can check for each and every code which one is cyclic, which one not cyclic. Okay. So the concept is that why I am introducing cyclic code concept here, because gray code is actually the cyclic code. Okay, among all these codes, only the gray code here is the cyclic code. You can check by yourself. Okay, so gray code is the example of cyclic code. So the gray code is not a weighted code. Okay, so but it is cyclic. So that means it is not used in the arithmetic operation, but it has used in other kind of applications. So we'll see where it will use. And one important note is that, so there is a particular method how we can calculate gray code from binary. But if you see the combination of gray code, okay, see the combinations of gray code, what you can take a note from this. If you, so what will be your note? So first is 0 0 0 0. Yes, the Hamming distance is 1. Exactly, the Hamming distance is constant here. So the Hamming distance is 1. So whenever you are taking any combination, you take 4 5, you take 6 7, So you will see there is only one bit positions will change. One bit position will change. Okay, so that means Hamming distance is 1. So and as there is only one bit position is changed when you are going to consecute, it means you are going sequentially from 0 to 1, 1 to 2, 2 to 3 like this. That means there is less number of chance of, means suppose you are using this code for means a purpose of trying, means in digital system, what you see in digital system, if any number of bits, suppose in a binary combination, if the number of bits are changing arbitrarily, means at suppose from going 0 to 1, one bit is changed, but suppose 3 to 4, two bits are changing. Okay, then say 6 to 7, three bits are changing. If these kind of things are happening in a particular code, when you realize that, when you apply that code in a system, in live system, in a computer system, then what actually happened, the power consumption of the system will increase. Power consumption means means that means the supply of voltage. So you need to change, means you need to give more supply sometime. You need to give less supply sometime, means you need to fluctuate very rapidly. You need to fluctuate very rapidly. For 4-bit binary combination, whenever there is 1, that means there is a 5-volt supply. Whenever there is 0, there is ground voltage, means 0 voltage. So that means applying that supply voltage to number of bits is very abrupt or very arbitrary. Okay, means suppose you are going from 0 to 1, only one supply voltage supply line is required. But suppose you are going from 4 to 5, you see 4 to 5 is not good example. Okay, 7 to 8 is a good example. When you are going 7 to 8, then you need to ground 3 bits. Okay, that is already supplied, that is in the case of 7 0 1 1 1. So three last lines are having 5-volt voltage, but when you are going 7 to 8, at that moment you need to make those line to ground voltage, and you need to make MSB line to connect to the supply voltage. Okay, so that means you need to do lots of work. Okay, what kind of work you need to do? So work means what? Power consume, you are consuming that system power more, you are utilizing more power. Okay, not utilizing, you are consuming more power. Okay, that means power consumption is high in case of this binary codes, but in case of gray code, the consumption of power is very low. That is actually always the advantage, always the aim of any system. Whenever you are using AC or fridge, what will be your looking? Your looking is how many units it will consume in a particular 24 hours. Okay, when you see a machine that will consume very less power, that will be an efficient system. So this is the way, if you think that how many means the power consumption for binary code is greater than the gray code. So that is the most advantage of the gray code. That means the gray code actually not used in any arithmetic operation, but these gray codes are used where the power consumption is required, less power consumption is required. In those scenarios, this gray code will use. Okay, so we'll see that scenarios just after some time. Okay, so here the binary to gray code conversion. Okay, so there is a particular method for binary to gray code conversion. Okay, so what is that method? Suppose a binary number is given 1011. Okay, so you need to convert it to the gray code. So what you have to do? First, you need to take the MSB and put the MSB. So 4-bit binary combination give you 4-bit gray code combination. So first bit is your MSB. So this is your MSB. Let me magnify this part first. So okay. Take this to mind. Okay, so this is the binary number 101. Now you need to take convert it to gray code. So you get, so first this MSB will be copied to this binary MSB copied to gray MSB. Okay, so what will be the next step? The number is binary is the same. Now the next step is, so when you're getting this one, so next you need to add this to one. Next you need to add this 2 digit. Okay, so what you get? 1 plus 0 1. So you write it down in the second position. Okay. So this is 1. So this 1 is coming from addition of these two yellow marked digits. Okay. So next is what? This 0 and 1. So this 0 and add 0 and 1, what you will get, you will see, you get this 1. Okay. Again, what will be the next one? Add this two digit. Okay. So then 1 plus 1. So you are getting 0. But also you are getting a carry. So what about carry? Just omit that thing. Carry you don't need to consider. Okay. This is how we can convert any binary number into gray code. First MSB is copied, then add consecutive digits in the binary. So 1 plus 0 will give you the second, 0 plus 1 this to give you the next one, then last two digits will give you this one. Okay. So this is how I can convert the binary number to gray code. Okay. So again here, gray code to binary. Gray code to binary. What happened? Gray code is given. Okay. So this is your gray code. So first is what? MSB will be copied. So same first step is always same. MSB has been copied here. What will be next one? Next is what you are getting in the binary position 1. Okay. You need to add this one to next digit of the gray code. Okay. So that means here I have to underline this one. So I'm underlining this one. So these two underlined bits are added. Okay. So 1 plus 1. So after addition 1 plus 1, what will get? 0. So this 0 has come here. Okay. Once you get 0, I underline this one. Okay. So what you need to do, you need to again add, sum this underline position bits 0 and 1. So 0 plus 1, what will get? Again 1. So that 1 is here. So again, when you get this 1, so you have already added with this one. So next one, what you have to add? 1 with this one. Okay. Just 1 second. Yeah, I'm repeating. I think I have made a mistake here. 1 plus 1, that is 0. 0. Oh, that is nice. I have already underlined this one. This bit is completed. So not this bit. Yes. Okay. So suppose gray code is given. Yes, gray code is given. Gray code is 1110. So first is you need to copy the MSB to binary MSB. Gray code MSB, binary MSB same. Next, you need to add, after copying these two value, you need to add those underlined bits. Underline 1, and here second bit is underlined. So underline 1, adding 1, you are getting 0 here. Again, this one is underlined 0, and you have already considered this MSB, means this position bit, second this underline position bit. So next bit is again 1. So 0 plus 1, you are getting what? Again 1. So this is underlined. Then 1. So this up to this is covered. So 1 is only 1 is left. That is this 0 is left. So this is again underlined. So 1 with this 0, 1 plus 0, what you will get? This this bit you will get, final bit. This is again underlined. Okay. So means the difference is when you are converting a binary to gray, you are adding each consecutive digits of binary, right? After just copying the MSB, you are adding consecutive digits. 1 plus 0, so you are getting 1. So 1 plus 0, you are getting 1. 0 plus 1, you are getting 1. 1 plus 1, you are getting 0. Okay. And now when I am converting gray code to binary, okay, same example, 1110, and so that means what I get, I get a 1011. So after copying the MSB, what you need to do here, again addition is required, but the addition is not consecutive bits of gray code, it is binary with gray. So you see this binary with gray. So if I give a arrow format, then it will be easy to give a arrow here. Okay, so is it mm, bold? Yes. So this is actually happening. Okay, so this again, so this with this, okay, you understand now. So this is how the things will go. Okay, so in grade 2 binary combination, this is the format of addition, but binary to gray, consecutive digits of binary will be added. Okay, so Sweta, I think this is the answer. Nilanjan, I have given the answer. So the application of gray code. So you see, I have already spoken to you application of gray code, and there is some examples. And finally, last one. Okay, this is the last one, the alphanumeric codes. Okay, so uh, just for the application, one thing I just want to give you the application part. The gray code actually used in the transmission of digital signals, where it minimizes the occurrence of error, because only one bit will change, so occurrence of error is always less. Gray code is performed over the straight binary code in angle measuring system. Okay, so this is also a very useful method for angle measuring system. Okay, gray code is used for labeling the axis in Carnot map. Okay, so that is used for graphical representation or for minimization of Boolean expression. Gray code is also used as address program memory in computer. Okay, so this is a real example. You can see these are the theory. This is also a real example, but this is also example related to your stream. So in the program memory, address of the program memory in your computer are stored in the gray code form. Okay, because this is due to fewer address line changing state with advances in the program of counter. Okay, because if I use gray code as a program memory in computer, then it will minimize the power consumption, because fewer address line change will occur, right, as we increase advance in the program counter value. Gray codes also very useful on genetic algorithm. Okay, so there are different kind of application of gray codes, and there is example try the problem I have given. Okay, answer is also there, so you try by yourself. Okay, the last one is alphanumeric codes. So here the alphanumeric codes means that the thing that I was discussing, that you need to represent different symbols. There are 26 English alphabets. There are symbols like this. Okay, so there is a code, so that code actually is your 7-bit ASCII code. So this is actually the code, which is nothing but alphanumeric code. This is actually the American standard code for information interchange. So it is an international brand. Okay, using this brand required takes 7-bit code. This is a 7-bit code. So this brand is used 7-bit code. So using 7-bit, it can represent total 128 different characters. So among those characters, there are decimal numbers. Okay, there are decimal numbers. So decimal numbers, we know that only 4 bits are required, but here it is 7-bit. So what about other 3 bits? So other 3 bits always 011 for any BCD number. So that thing is written here, and other also, as well as means alphabet, uppercase, lowercase, other symbols are represented in this format. Okay, and in this format, so that is the thing. In this here, you after getting the information of BCD code, gray code, XS3 code, you need to take the information of this code also. Okay, so using BCD, gray code, or XS3 code, we can represent a decimal numbers. We are talking about everything. Whatever we are talking about decimal numbers. So finally, here in this position, we are talking about the special symbols, the alphabets, uppercase, lowercase. Okay, so for this purpose you require 7-bit ASCII code. This is known as ASCII code, American Standard Code for Information Interchange. Is an international brand. It uses 7-bit code. It can be used to represent 128 different characters, among them the decimal numbers 0 and 9, that is represented by 8421 BCD code format. And what about other 3 bits? 0 bits are 011. Okay, so basically that this is all about the codes. So this is the end of the first chapter here. So to sum up, here we understand different codes, different number system, different code conversion method, different number system conversion method, different representation of integer floating point in different number systems. Okay, so there are lots of information I have given to you in this chapter. So what you have to do, you need to practice more the examples that I have given here in my notes, or you can take help from any book also. Okay, so that you can grab the knowledge of this chapter. Okay, this chapter is very much important to start with digital system. Okay, next chapter I will discuss that about your logical gates and their combinations. Okay, that will start from the next class. Okay, so today up to this. So everyone, for this session you need to write down your ID, and if you have any query, then please ask me here. So
सर एक बार बाइनरी टू ग्रे और ग्रे टू बाइनरी वापस एक्सप्लेन करेंगे?
देखो, binary to gray. So what is actually gray code? This is the BCD code I have started. XS3 code. This is the gray code. So binary to gray, gray to binary. Okay, this one. Okay, so basically I have shown you the method that yellow marked digit is copied first, that is MSB. Then consecutive bits will be added. So consecutive bits means I have highlighted 1 0. So addition 1 0 give you 1. So I have noted 1 here. Okay, so binary to gray is quite easy because here consecutive bits of the binary will be added. So 1 0 give you 1, 0 1 give you 1, 1 1 give you 0. So what you are getting finally, here you see you are getting 1 1 1 0. But in case of gray to binary, this addition actually follow this arrowhead location. You see, bit by bit position. So first you copied the copied number, copied bit is added with the second bit of the gray code. Then you are getting the second bit in binary, that will be added with the third bit of the gray code. Then you are getting the third bit, that third bit will be added with the final bit of the gray code. So let me just again copy paste. So this will be added with the final bit of the gray code. So when you add 1 plus 0,
वन
okay,
प्लस वन तो वन, हेलो
हाँ हाँ बोलो, 1 plus
सर,
1
इसमें
is 0.
कैरी हम लोग कंसिडर करेंगे क्या?
No, carry is not considered here. ठीक है, ओके चलो
ओके,
फिर.
दैट्स
हम्म. Okay, so okay, up to this. So just session will end within 5 minutes. So just don't forget to write your ID here. Okay, so I'm stop sharing this document.